Thanks everyone for joining. We're gonna get started. Folks are still coming in. If you're still on your way in, that's not a problem. Make yourself comfortable, and we'll kick this off. We're gonna start with a little bit of housekeeping. So just so everyone knows, there'll be plenty of time for questions at the end. So if you have questions, you can add them at any time, and we'll get to them at the end. And we are recording this session. And we've also recorded the previous 3 sessions. So if you have to drop off early, or if you feel like you missed out on one of the earlier sessions, don't worry. We'll be sending you a link to all of them. So I want to introduce myself. My name is Daniel Mintz. I'm the Chief Data Evangelist at Looker, the analytics platform. And we are the authors of the Pocket Guide to Databases. We at Looker work with dozens of databases and data warehouses and data engines. And so by necessity, we have a ton of knowledge about those databases, what they do really well, what they're maybe not so good for inside our organization. And we wanted to make that available to the world. So that's where the Pocket Guide to Databases came from. If you haven't already checked it out, I highly recommend it. It's at databases.looker.com. And today will be the 4th and final session of our database bootcamp. Today I'm going to be talking about the future of database technology. So just to sort of review, and as I said, don't worry if you've missed some of these, since you can catch them on video. But last week I kicked us off with the introduction to databases, where we talked about sort of a little bit about how databases have evolved over time and what different kinds of databases there are, what they're generally used for, what they're good for, what they're not so good for. And then as the second event last Thursday, Kenny Cunanan kicked off our deeper dives by going into transactional databases. So you know, all of the different kinds of transactional databases that process transactions that are generally used for running production systems, whether that be a bank or a website. On Tuesday, Kenny came back and dove into analytical databases. So, you know, talking about what are the kinds of databases that excel at, you know, analyzing vast quantities of data. And you know, that those 2 main work types, transactions and analysis, are the sort of 2 biggest things that databases are used for. And so we wanted to sort of cover those in a little bit of depth so that you had a nice foundation on both of those types and, you know, what some of the players in each space are. Today, I'm going to be talking about the future of databases. You know, so where do we see databases going? You know, there's been tremendous development in the world of databases, even over the last 5 or 10 years. You know, if you joined my first session on the introduction to databases, you might remember that we talked about sort of, you know, the advent of big data, which happened sort of in the early 2000s with the beginnings of the Hadoop MapReduce ecosystem. And then, you know, in the last 5 years, there's been this explosion of cloud data warehouses, cloud transactional databases. You know, the cloud has really accelerated the pace of change. And so there are just amazing new things happening in the database world. And so that's what I'm going to be talking about today, not just what we're seeing today, but, you know, sort of what we expect to see tomorrow. And then, you know, what are the reactions that we might have? What are the things that we might want to be able to do with these new databases and these new technologies that we can't currently do? So I'm actually going to focus in today on 3 specific databases that you may have heard about, especially if you attended the last boot camp on Tuesday, where Kenny talked about analytic databases, because these are 3 very popular analytic databases. They're all on demand, meaning that you don't need to sort of reserve them in advance. You don't need to buy the servers that run them. They're all running in the cloud. And so one is from Amazon, that's Redshift. One is from Google, that's BigQuery. And then one is an independent company called Snowflake. And so these are all MPP databases, meaning that they're all massively parallel systems. They can run queries across many, many servers at once, spread that job out so that it can be accomplished very quickly and very efficiently and cost effectively. So as a first piece, I just wanted to sort of give a little bit of a deeper background on each of these databases so that we have sort of a good understanding of what they are as a jumping off point. So I'm going to start with Amazon Redshift. Amazon Redshift was released to the world in 2013. And really it was the first, I would say, major player in the sort of cloud MPP space that really gained a foothold. Amazon and their AWS ecosystem is gigantic. They have, tens of thousands, hundreds of thousands of companies using it. And so when they rolled out a real powerful cloud data warehouse as part of that ecosystem, people jumped on. And so Amazon has had, enormous pickup of Redshift. I know at one point it was their single fastest growing service. Amazon Redshift is highly tunable. So there's lots of sort of ways, knobs that you can twiddle to make Amazon, have Redshift go faster. That's everything from the types of nodes that you choose, whether they're sort of big hard drives with, that are spinning drives with less powerful compute, or really, really fast solid state drives that have less storage but are incredibly fast. And that's sort of the highest level tuning, but you can really go down into the weeds and do a ton of tuning if you have the knowledge how to do that and get really amazing performance out of Redshift. Redshift is based on a technology called Parcel, which was an MPP data warehouse. And so Amazon took Parcel and sort of jumped off from that and built Redshift on top. And as I said, Redshift lives inside the AWS ecosystem, the Amazon Web Services ecosystem, and that is a huge ecosystem of dozens, maybe hundreds of different services. And because Redshift lives in that ecosystem, it can take advantage of all of its sort of connections with those other pieces. So, it's not just a data warehouse and then you have to go somewhere else to get your compute capacity and your storage and your data pipelining and your Hadoop MapReduce. All that stuff is available right within the Amazon ecosystem and lots more. One thing to know about Amazon and AWS, if you've used AWS for any length of time, you've probably noticed this, but Amazon just keeps making these products better and cheaper. You regularly get notifications that, hey, that thing that you're paying for, we're going to just keep giving you that same service, but we're going to make it cheaper. Or, hey, that thing that you're paying, $1 for an hour, now it's just going to be a faster machine. So Amazon is constantly improving the hardware and technology underneath this. And the way that Redshift charges is you pay per node. So a node is part of a cluster of servers that that run Redshift for you. And so the more nodes that you add, the more powerful Redshift becomes, the faster it can run queries on larger data sets. But what you're doing is paying for each of those nodes, and you can pay them hourly, or you can reserve them for a year or up to 3 years for discounts. So that's a little bit of background about Redshift. Now let me dive into BigQuery. So BigQuery was actually released in 2011 by Google, so before Redshift came out, but it really didn't catch on, I would say, until the last 2 or 3 years. Google has made a huge investment in GCP, the Google Cloud Platform, recently, and that has coincided with a real focus on BigQuery and getting more and more companies onto it. It is based on Dremel, so BigQuery is not based on an external technology, but rather on an internal Google technology. And a lot of Google's products come this way, where even Gmail was a mail product that was built for internal use by somebody with their 20% time, where they were sort of goofing off. They wanted a better mail client, and they built what became Gmail. And so the same thing happened with BigQuery, where they had this internal system. They had lots and lots of data, as you would expect Google does. They needed a way to ask questions of it. Dremel was what they built to do that. And eventually they said, hey, this is a really powerful tool. I bet other people would like having access to this. So maybe we should turn this into BigQuery and make it available publicly. And that's what they did. BigQuery is really a no operation data store, in the sense that you don't have to spin up an instance of BigQuery. You don't have to provision BigQuery ahead of time. You just log on and go. Google does all the operations management in the background for you. So there are not multiple instances of BigQuery. There is one giant global instance of BigQuery. You just log on to that. It knows where you tell it where your data is for it to access, and it starts querying it, and that's it. So that's pretty neat. And it actually scales computing resources per query. So it's not that you have a fixed capacity. It's rather that you, when you send your query to BigQuery, it judges how hard that query is and how many compute resources it will take, and then grabs the right number from its giant pool of resources that are available to sort of all of the BigQuery users at once. BigQuery does some neat things in terms of types of data that it can accept. So this isn't unique, but it is one of the rarer features that BigQuery offers. It can deal with nested data, so data that's sort of organized hierarchically often has to be what's called flattened to put into a relational database. But BigQuery doesn't require you to do that. If you want to leave that data nested, that's fine, and BigQuery can handle that. And lastly, just in terms of how BigQuery charges, it actually, you pay per query on BigQuery. So the more queries you run, the more you will pay, and the more data you're processing in those queries, the more expensive those queries will be. There's lots of tools as part of BigQuery that allow you to sort of do cost control, so you can limit how much any given user or your company can spend, so you don't overspend. But unlike Redshift, where you're kind of paying for a fixed capacity, and your costs are fixed, but your capacity is also fixed, BigQuery is dynamic. So your bill might vary month to month based on how much you're querying, but it also means that you kind of have unlimited resources at your disposal. So the third database technology I want to talk about is Snowflake. So Snowflake sort of came out publicly out of stealth mode in 2014, so it's kind of the third on the scene of these three. And unlike BigQuery, which is based on Dremel, or Redshift, which is based on Parcel, Snowflake was architected from the ground up to be a cloud data warehouse. It is a sort of different breed. I don't think really there are any other tools out there that this is true of, where the company was founded just to build this cloud data warehouse. There's sort of a seminal, important research paper where the engineers at Snowflake laid out their architecture, and that's really the core technology at Snowflake. It's not part of its own ecosystem the way that Google and Amazon have their ecosystem. Snowflake is an independent company that just does data warehousing. One of the key features that Snowflake's unique architecture gives them is that it actually uses Amazon's S3, which is Amazon's kind of unlimited hard drive in the cloud storage. It uses S3 to store the data, but it has compute capabilities. Snowflake has compute capabilities that aim at that data that lives in S3, and they can scale independently. And so what that means is that you can say, we have this big job that we need to manage, or hey, it's the holidays and we're processing more orders, we need more compute capability to crunch through that data faster. You can scale that up separately from the storage layer that lives in S3. And in fact, you can do more than that, because you can actually point multiple compute centers at the same data. And like BigQuery handles nested data, Snowflake is actually quite good at handling semi-structured data, so like JSON data. Snowflake has a lot of specific functionality for dealing with that kind of data, so that's another nice feature of it. As I said, it runs entirely on the AWS cloud, so the data lives in S3 for storage, and it's using EC2 compute resources. And you're paying based on storage and usage, so you pay some storage cost for the amount of data that you're storing, and then you're paying based on how many what they call virtual data warehouses and virtual clusters you have spun up at any given time. And so if you spin up a bunch of warehouses to get through a particular job, you can spin the ones that you're not using back down and stop paying for them. So that's a little bit of background about those three. And they're all pretty amazing technologies. We work very closely with all three vendors. And, the thing that you will notice if you are using these is that there are some things that they are just getting better at every day. Maybe that's an exaggeration, but every month or two, it seems like one of them rolls out some big new feature that kind of falls into one of three buckets. Partially, they just get faster. They are able to throw more and more powerful servers at the problem, and they're able to do it for less money. So, as computers get faster and faster, as memory gets cheaper and cheaper, as hard drives get bigger and bigger, they are just getting better and better because they benefit from all of that, those improvements in hardware. So, they're getting faster, they're getting cheaper, and they can store more and more data. So that's really great. But, and this is really where I want to focus most of today's talk, there are some things that bedevil those of us who deal with data that actually aren't getting better automatically. And so I really want to dig into three specific things that aren't getting better automatically. So one thing is that data movement is not getting better automatically. And particularly as we are collecting more and more data, more and more business data, moving all of that data from place to place is becoming a bigger and bigger challenge. Now, there's no question that it has gotten better since the days of not having serious networks, and so needing to actually ship physical drives or tapes from place to place. It's definitely gotten better since then. You can, take advantage of the internet and move this data from place to place across the internet. But the reality is the quantities of data that we're dealing with often still are far too big to go through the pipes that make up the internet. And it's a great example of that. A couple of years ago at AWS reInvent, their giant conference in Las Vegas, they talked about a new service for migrating enterprise level data to their cloud. And when you were dealing with the amounts of data that some of these companies were dealing with, piping that data through the internet or through networks would have taken literally years to move all the data. And so Amazon introduced the Snowmobile, drove it onto stage. It's an 18-wheeler, an actual 18-wheeler, full of hard drives. And so their migration path, the only sort of reasonable migration path to move all of the data that some of these companies were dealing with was literally to drive a semi, a tractor trailer to your existing data center, move all of that data onto the hard drives, protected by armed guards, and then drive it to their data center where it would be trucked off. So this problem of data movement, most of us, I would say, are probably not dealing with the scales of data where we need tractor trailers to move it. But the reality is, even for those of us dealing with smaller amounts of data, moving that data continues to be a challenge, and something that that these databases aren't sort of solving on their own automatically, just by getting faster. So another thing that's closely related to that is latency. Data originates in one place. It's produced by one source system, and usually we're then trying to load it into our data warehouse. And moving that data, as I said, is hard, but not only is it hard, it takes time. And so what that means is by the time the data gets to its destination and you're ready to run queries against it, it's late. Time has passed, and so the data is about the past. Now, again, latency has often gotten better, but there are tons and tons of companies that are still on a 24-hour ETL cycle, meaning that the data doesn't make it into their data warehouse until at least 24 hours after the thing has happened in the real world that the data is recording. And some, are still on longer ETL cycles than that. So this idea of latency, even if you're, running a relatively fast data pipeline and moving the data into these warehouses, on the order of minutes or hours, that's great, but it's still, the data is late by the time it gets there. And then the third kind of problem that's not really getting better is the problem of siloization or decentralization. And this, I actually think it's a place where not only is it not getting better, but I think it's actually getting worse. And the reason for that is more and more systems are creating data, and the most useful analyses almost always need to combine data from multiple places or multiple data sources. And so the fact of having 10 SaaS applications that you use on a regular basis, plus your web traffic data, plus your transactional database data, plus whatever else you're tracking, the problem of having all of that data locked up in each of those source systems and not having it in a single place where you can access it and join that data is becoming a bigger problem, not a smaller one. It's impeding good analysis, because the reality is, if you really want to understand a customer and their interaction with your website, you need data from the website for sure, but you also need data from the sales system that recorded if they bought anything. And you probably could use data from your sales support, from your help desk, to see, well, are they making use of that? It might look like they're having a great time and purchasing things, but maybe they used hours of support to make that happen, right? And so to really get a view of what is happening, you need data from multiple places, and you need it all in the same place. And so the solution to this today, the solution to all three of these problems, data movement, data latency, and data decentralization, is just a big mess of pipes. So the way that people deal with this today is by connecting pipes of varying shapes and sizes and complexity to all of their data sources and lugging that data into a warehouse, some central database where they can access it all. But moving the data is hard. The data, it takes time to move through the pipeline, and so by the time it's there, it's late. And maintaining these pipes is really hard. Having supervised and built data pipelines myself, I can just tell you it's really a bit of a nightmare. These systems become increasingly and almost unmanageably complex very quickly. They break relatively frequently. The source systems that are sending you data often change the format of the data that they're sending you without warning, and so you have to adapt to that. So it's quite a major headache. And so, that's the system today, that's the situation today, but I think when we look at the future, I think the future looks like data that sort of is magically just there. It doesn't need to move. Because it doesn't need to move, it isn't late, or it's much less late. The amount of time it takes to get where it's going is much lower. And the decentralization of data, I think we will see diminish as more of this data becomes available in sort of centrally available places, so that you can access it without having to move it around. So those are my predictions, but those are not, I'm not just pulling those out of thin air. I want to talk about how the three databases that we touched on earlier, how they're actually doing parts of this already, because I think that's really part of what makes all three of these, Snowflake, BigQuery, and Redshift, so interesting, is that they're all moving in this direction of data that's just there, that's there instantly, and that's centralized. So I want to touch on the way that each of them are tackling these problems, because I think they're different, but they all point in the same direction. So let's start with Redshift. So, Redshift, as I said, is a cloud data warehouse. It's an MPP data warehouse where you load data in. You can do that very quickly because you can parallelize the process so that the data gets sort of sucked in by many different machines at once. And then you can query it. But most companies that are using Redshift probably also have enormous amounts of data that are not nicely sort of curated and shaped and ready for loading into Redshift, but actually just live in S3, live in Amazon's giant cloud hard drive. And so Amazon, seeing this, realized that there was an opportunity, and they said, you shouldn't have to move your data into Redshift to query it. You should be able to query it right where it lives, right in S3, without doing any reshaping or any movement. And so they rolled out Amazon Athena recently. I think it was about a year ago, to do exactly that. So Amazon Athena is an implementation of the Presto data engine. So Presto was originally built at Facebook as a sort of proprietary solution for querying their data. It was then open sourced, but it is this very powerful data engine that can access data that just lives in files in storage without having to load it like a data warehouse. And so Amazon Athena took that engine and made it work on S3. And so what this means now is that companies don't have to move their data. They don't have to wait for that data to get into Redshift, and they don't even have to worry about decentralizing it, because the reality is most companies that use S3 are using it as sort of a data lake where they just dump everything in. And so if you've dumped everything into the lake, it's all there. You don't have to worry about it being decentralized. And so Athena gives them the ability to access all of that data directly on S3 without loading it in. And Amazon went even further. They took it a step further more recently by saying, well, Amazon Redshift is great. It's a very powerful cloud data warehouse. And Amazon Athena is great. It's a very powerful data engine that you can use on S3 data. But it would be really nice if you could use those two things side by side, if you could use them as one. And so that's what Amazon Redshift Spectrum is. So what it allows you to do is to basically access that S3 data, run queries against that S3 data right from within Redshift. And so that's what Spectrum gives you the ability to do. And so it means that, whether the data has been loaded into Redshift or the data still lives in S3, you can run a query against both of those pieces of data simultaneously and from the same spot. And so that's a really powerful technology, a very sort of interesting, smart way of addressing these problems of movement, latency, and decentralization that Amazon has taken. So next I want to talk about a service that Google rolled out called their BigQuery data transfer service. So this is solving or addressing similar problems, solving a pretty specific one, but one that is shared by tons and tons and tons of companies. So Google, as you may know, owns quite a few of the major tools that marketers and companies use on a daily basis. So that includes things like Google Analytics, YouTube, DoubleClick for publishers, and AdWords. These major, huge web properties that are used by businesses. And all of those tools create a ton of data. And that's data that sometimes is available right within the tool in sort of pre-built reports and dashboards, but not raw. And so that limits the amount of analysis that companies can do of this data. And so what Google did was they said, well, we have all of these data producing apps that people are using a lot. People are hungry for this data. They want to be doing more custom analysis, deeper dives into this data. And we have BigQuery now, which is this immensely powerful data warehouse. We should make it really easy to get the raw data from these services right into BigQuery. And that's what the BigQuery data transfer service does. That core problem of moving the data and building those pipelines, Google made it go away. And they made it go away by saying, if you would like the data from these services in your BigQuery instance, just tell us and we will move it. And so they take care of the extraction of the data from the source system, the transformation that's necessary, and the loading for you. They just make it happen, and it shows up in BigQuery, and then you can query it to your heart's content. So Google saw a very specific problem, but one that is shared by so many companies because so many companies use these different services, and they came up with a really elegant solution by taking away all the pain that is normally involved in getting this data available. So instead of paying an external vendor that would charge you a bunch of money to do some kind of extraction process through the API, Google said, well, we just have the raw data. We'll push it right where it needs to go, and it'll be available to you. And actually, just to touch on our partnership at Looker with BigQuery. We actually worked with Google to develop what we call Looker blocks. So Looker, because it sits directly on top of BigQuery, once this raw data is available in BigQuery, that's amazing, and it means you can do any analysis that you can dream up on this data. But the shape of the data may not be something that you're familiar with. You may not really understand the way that Google Analytics data is nested, and so it can be a real slog to make that data queryable and turn it into the kinds of reports and dashboards and explorations that you want to do. But we at Looker know exactly how it's shaped because it's always sort of shaped the same way, and we've solved that problem for lots of customers. So what we did was we packaged up the data code that was necessary to reshape that data, to turn it into pre-built dashboards and reports, and we make that available as part of Looker. So those Looker blocks are available for all of the BigQuery data transfer service sources so that you can be up and running immediately. Google puts the data where you can access it in BigQuery. Looker sits on top of BigQuery, pre-built blocks, and you're off to the races. So BigQuery data transfer service, a second interesting way that people are tackling these core problems that we still face in data. And so the third one, oops, that is a mistake. That should say Snowflake in the top left. Sorry about that. A third one I want to touch on is Snowflake. So Snowflake, as I said earlier, is a unique architecture, and that allows them to do some really neat stuff since they're sort of building from the ground up. And one of the really cool things that they've just rolled out is what they call the data share house. And so if you remember back to when I was talking about Snowflake, Snowflake, they separate the compute layer and the storage layer. And so that means, you can store your data once, but query it from, 1 or 2 or 5 or 10 different warehouses simultaneously, because each of those compute servers that is pointing at the stored data is independent and can all access that same stored data without having to copy the data to a bunch of different warehouses. But what the data share house lets you do is they said, well, if you internally could have 10 different virtual warehouses, virtual clusters pointing at that same data, why not make it so that you could actually share that externally? Warehouses. It means that one Snowflake customer can share their data, the storage layer that is holding their data, with some other customer, and that customer can then query that data directly. So if you're a company that serves other companies and you have customers and partners that you would like to make data available to, now you can do that using the Snowflake data share house without having to move that data, without introducing the latency of moving that data. And that other company can now query your data right alongside their data. So all of a sudden they've gone from having it decentralized because some of that data lives with you and some of it lives with them, to being able to query it side by side because, well, it all lives in Snowflake. All that data lives in S3, and so it should all be queryable side by side. So, I think when I think about sort of analogs to this model, I think of it very much as going from having like a Word document that multiple people are working on, and so there's a ton of different copies of the Word document that are floating around in email, and it means knowing if you have the latest version is a real headache because, oh, I sent it to you, but then I kept making changes, and now you've made changes, and now we have to integrate those changes. And now it's much more akin to like Google Docs, where there's a single version, it lives in the cloud, everyone's accessing the same version. There's no need to move it, there's no need to wait. And so that's very much what Snowflake has been doing with the data share house, and I think very much also what Google BigQuery and Amazon Redshift have been doing with Athena and Spectrum and the BigQuery data transfer service. So, those are sort of 3 just examples, not chosen at random, but 3 of the most interesting examples, I think, of the way that some of the smartest players in this space are tackling the ongoing challenges in databases and data warehouses. And I think it would be I'd be missing a major piece if I just stopped there by saying, well, these are some cool things that are happening. I think the real question always is, well, what are the implications? We don't play with data for the heck of it. We don't play with it simply to amuse ourselves. We play with it because we're trying to get value from that, whether that's research value or study value or business value. We're trying to get get value from it. And I think, when you look at the databases and data warehouses getting faster and faster and cheaper, and you look at these problems of movement, latency, and decentralization starting to get solved or addressed, I think it's important to think about what that means. So one thing that it means is we can get closer and closer to real-time analysis. Now, I think when people say, I want real-time data, my question is always, well, what does real-time mean to you? Because, real-time could mean I need sub-second data. The thing happens and in less than a second I need access, or it could mean I need it within a minute or 10 minutes or an hour. Usually when people say real-time, what they actually mean is just less than 24 hours. So, I think it doesn't need to be that we're getting to real time meaning instant, but I think as we get closer and closer to that instant data, what it allows us to do is to do more operational analytics, where rather than just doing historical analysis and looking at what happened yesterday or the day before, we can look at things pretty much as they're happening and react to them as they're happening and make operational decisions as they're happening based on data. And so I think that's really exciting. We at Looker have tons of customers that are using Looker operationally, on a factory floor or in a warehouse, or in a medical setting where they're looking at the data, as it's coming in and making better decisions using it. So that's one big thing. Another implication, I think, is that we can make data available to lots more people within an organization, which is really important. Because there are lots more people today who want data, who see data as part of their daily lives, their daily jobs. And, the way that data warehouses existed 20 or 30 years ago, or even 15 years ago, was in a state of sort of perpetual fear that they would be overloaded. And, so you were constantly doing things to protect these databases from too many users because they would ask too many questions and the database would go down. And while that fear hasn't completely gone away, I do think that these on-demand, these elastic cloud warehouses that are just far more powerful than anything anybody imagined 20 years ago, they make a whole new world possible where you can give access to the customer success manager and the growth hacker and the DevOps engineer, because the reality is all of those people are data workers. They're all people who want access to data because it will let them do their jobs better. And we don't need to cut them off or give them only Excel spreadsheets. We can really let them at the raw data more. And then the third implication, I think, is that we can start thinking about bigger and better and more sort of better suited tools for all of these different people who access data. So it doesn't just have to be the hammer of a dashboard. The reality is we can now build a much richer toolkit that lets people access data, right in their workflows in interfaces that are comfortable to them and intuitive to them. And by giving people access to that data, I think they're much likelier to use it and to use it well, so that they're really getting benefit from it. So that wraps us up. That is the end of the bootcamp. If you've done all of them, you've covered our introduction to databases, our transactional database overview, our analytical database overview, and then today with me, our future of databases. You did it, and even if you didn't do it because you missed one or more of these, don't worry. As I said at the beginning, we'll be sending you recordings of all of them so that you can go back and catch up on any that you missed. Before I jump to questions, I just want to remind folks, if you haven't checked out the Pocket Guide to Databases, it's an incredibly informative resource that we put out there really just because we think it's valuable and we want people to have this information. So databases.looker.com. If you want to know more about Looker or see a demo, you can always visit us at looker.com/demo or email us at discover@looker.com. And with that, I'm going to jump over to any questions. So if you have any questions, just click on the Q&A button and you can enter your question and I will do my best to answer it. So starting off, so this is a good question. Is Athena a replacement for Redshift? That's a great question. So just to remind you, Athena is the Amazon technology that lets you query data directly where it lives on S3. It is now sort of built into Redshift in some sense as well through Redshift Spectrum. And no, I don't actually see Athena or Spectrum, the Spectrum part of Redshift, as a real replacement for Redshift. I still think that for the purposes of the data that you're querying most often, Redshift is probably the right tool. But I think where Athena really shines is that it saves an enormous amount of time when you're sort of prototyping or querying data that you don't query that commonly, because it means you don't have to worry about the import step to get it into Redshift. And so I think what we see a lot of people do with Athena is they'll query some less frequently accessed data, maybe to understand if there's something there that's worth loading into Redshift, or to find the exact piece of data that they want to explore more deeply in Redshift. Maybe they're looking for some event that happened in their web logs and they want to find exactly when it happened, so they use Athena to narrow it down to the right day and then load that day's data into Redshift. So I think it's a great complement. I don't think that it's a replacement. I don't think Amazon actually sees it as a replacement. I just think it's they're two things that serve complementary functions and work really well together, especially with Spectrum. So I see a couple more questions. So this one says, I've heard Snowflake is particularly good at concurrency. What exactly does that mean? That's a great question. So when we work with Snowflake, that very much sort of jives with our experience of Snowflake. Snowflake, because of the ability to keep compute and storage separate and the ability to spin up multiple virtual clusters that are all pointing at the same storage data, it can actually support huge numbers of users querying the same data at the same time before showing any performance degradation at all. So if that sounds like your use case, where you have not just 10 or 50 or 100, but 500 or 1,000 or more users who are querying data at the same time, I think Snowflake is definitely worth giving a look at. It's a really great architecture for that particular use case. Another one just came in. What are some of the most common use cases you see for BigQuery? So I think BigQuery, because of its scale and because of its sort of ability to stay fast no matter how much data it's querying, because of the elasticity of the resources that it can devote to your query, is great for companies with large data sets. But I think with the introduction of the data transfer service, it's great for people who are coming in with data from one of those sources, Google Analytics or YouTube or AdWords or DoubleClick for publishers, because that data gets in there so easily. It's quite good for, we see like a lot of gaming companies using BigQuery because they have huge amounts of data where they're tracking, mobile game usage. So the ability to crunch through all of that data is really one of the things BigQuery excels at. And the fact that it scales automatically without your having to do anything or do any operations is a big win. I also think that customers who don't have a lot of DevOps resources and just want to get up and running very quickly, BigQuery is a pretty great way to do that because of that no ops feature. The fact that you just log in and go, you just load your data and go, don't have to spin anything up. There's no overhead. Is a pretty great feature. So what do you think the future, if any, of multi-dimensional cubes that usually run on top of on-premise data warehouses is? Great question. So for folks who aren't familiar, OLAP cubes are this concept that came about in data warehousing for allowing people to sort of slice data a bunch of different ways. So maybe if you wanted to see sales by store by date, you'd build cubes to do that, and then you might build another cube for sales by store by week, and sales by store by month. I think the initial reason for those to exist was really for performance. It was the only way that you were going to be able to access that data in a timely manner, and it saved time, because if you only needed the sort of monthly data, you didn't want to dive down into the daily data. So, I think for the most part, where we don't see people, and we don't recommend that people sort of import that particular way of doing things directly to the cloud. If you're building your schema from scratch and you don't already have, multi-dimensional cubes, I wouldn't recommend that you build them. Though, I think a lot of these cloud warehouses are pretty adept at handling cubed data. But I also don't think that cubes are sort of fully going away. I just think they're evolving a bit. And I think what you might start seeing is, tools that allow you to sort of dynamically move between cubes, so that, maybe you want the smaller data sets, the smaller cubes held in memory, and be able to access those super quickly and super cheaply, but hold the raw, event level detail on the hard drive. So, I think we at Looker are looking at a bunch of sort of ways to incorporate that same core concept into our technology, but I don't think, people aren't using cubes quite the same way, but I also don't think they're quite ready to go away yet. So another one, will Looker be doing additional series like this on various other BI topics? That's a great question. I know the response to this one has been tremendous. Thank you all for attending and participating and asking great questions. I think we will definitely be looking at it and trying to think what else we have knowledge about that we could offer. I love talking about this stuff. I know Kenny does too. So yeah, we'll definitely be looking at this and seeing if there are other options. But we really enjoyed it. So thanks for the feedback. And I think those are all the questions that have come in. I am happy to hang out for another couple of minutes. If anybody has any lingering questions, feel free to drop them in. But if not, have a great day. Thanks again for attending. I'll just put the slide up again. Check out the Pocket Guide for Databases. Send us an email, request a demo. We'd love to show you sort of how Looker works with all these technologies that we've talked about in the last couple of weeks. Thanks, everybody.